Hi everyone, my name is Bryan Acosta and I'll be doing question 35.
All right, question 35. So the question states the average person exhales 1 kilogram of carbon dioxide in a day. Estimate the number of carbon dioxide molecules exhaled per breath of this average person. Assume one breath takes 3 seconds. Okay, so immediately the problem says we have 1 kilogram of breath exhaled per day. So looking over here, I like to create this little nice flow chart that's going to describe exactly what we need to do to set this up. So 1 kilogram has to convert to 1 gram or 2 grams, and then to moles, and then finally molecules of CO2. So using this, we're going to create a dimensional analysis. We got 1 kilogram of breath is equal to 1,000 grams, which is 1 kilogram, and then the moles. So 1 mole is equal to 44.01 grams. And you're probably asking how I got that number. So if you take a look at your periodic table over here, you're going to have to find, remember our element or our compound is carbon dioxide. That's what we're exhaling. We got carbon right here. It's got a mass of 12.01. Dioxide, which means 2 oxygen, and it has a mass of 16. So of course, if we go back, carbon 12.01, oxygen 16, but carbon dioxide, so we multiply the 16 by 2 and we end up adding them together, and that's how we get the 44.01 grams. Let's go ahead and plug that in right there. And then this number is actually a given. You're probably going to find that on formulas and tests and other stuff like that, and you should be familiar with it if you're working in this unit. But this is Avogadro's constant, and it pretty much describes how many molecules per mole we have. So in a dimensional analysis, you're just going to grab what you're given, you're going to multiply by the top, and you're going to divide by the bottom. You just plug this into your calculator, and you're going to get 1.36 times 10 to the 25th. Now your calculator is going to give you a number. It's going to be pretty long, but of course you're going to have to convert that to scientific notation, and it's just going to be the number of significant figures of what they gave us times the 25th. But since this is actually just part of the problem, this isn't the legitimate answer just yet, it's fine if you actually leave it in the proper or the full form. You don't have to actually round that to significant figures just yet. But yeah, so this is the number of molecules of CO2 per day. Now we have to actually change the time, because we're not looking for per day, we're looking per breath, which is a subset of the time. So 1 day is equal to 24 hours. And from there, we're going to convert that to minutes and then to seconds. Once again, another dimensional analysis. And we're going to say 1 day, there's 24 hours in 1 day. There's 60 minutes in 1 hour. There's 60 seconds in 1 minute. And if you take a notice, you can actually see exactly what's going on here. The hours and the units on the top is being canceled out, and we're left with, let's see, if we cancel out the hours, then we cancel out the minutes, then we should be able to get the number of seconds per day. So moving on, this is exactly the number of seconds per day. We're gonna get what number we got from the top right over here. And we're gonna plug it in over the number of seconds in a day. And what this is doing is this is pretty much saying, okay, if we have molecules of carbon dioxide, we got the seconds, we're going to be able to get the molecules of carbon dioxide per second, right? But 1 breath is 3 seconds. So we actually need to multiply by that and divide by everything on the bottom. And you'll actually finally have your final answer of 4.75 times 10 to the 20 molecules of CO2 per breath.